I want to welcome you to another statistical topic. The focus today is going to be on variable selection. In statistical analysis, we basically want to actually figure out what are the important variables that should be included in our model. Okay, so what I'm going to be walking you through today is just to walk you through, you know, a kind of strategy that can actually be used to select most relevant variables. So in the outline, if you take a look at the first one, it said, can we have a way to improve on ordinary least square? Okay, because we live in a world, where we basically want to make an improvement. We can never be satisfied with what we got. You get what I mean, right? Then I'm also going to explain the difference between module complexity and module fitness. They are not the same. Okay. Some researchers in the past, the reason why they actually uh, took, a wrong decision is because of the fact that they only consider module fitness uh, instead of, putting into consideration module complexity as well. So today, I'm going to make a distinction between these two. Then from there, you're going to learn new module selection criteria that is different from the one you already know in module fitness. There's something called adjusted R squared, the AIC and the BIC. They are actually the metrics of evaluation of module when we take into consideration not only module fitness, but also module complexity. Then you're going to learn to procedure of variable selection. I told you the other time, we actually want to learn a strategy, okay, that will enable you to select most relevant predators in your model. And we actually have procedure, okay. We have two general, procedure that we use. The one we call the up-success selection and the stepwise selection. I'm going to walk you through all of that. Now, let's get started with the first objective of the day. Those of you online, can you still confirm? Are you still hearing me? Those of you online.
Yeah, we can hear you.
Okay, thank you so much for confirming that. Okay, can we improve on our ordinary least square? What do we call ordinary least square? The ordinary least square is a method that we use in estimating parameters, the linear regression parameters, when you assume a linear model. Now, let me tell you this. We got condition under which the ordinary least square approach work. Okay, the ordinary least square is what we also denote as OLS. You see OLS, right? Now, when the number of observations is much more greater than the numbers of predators, n, the lowercase n, is the number of observations. Okay, the number, the lowercase n, okay, that is a number of observations, okay, and p, okay, is the number of predators. Okay, when I say predators, I mean explanatory variables. Okay, now, so that is the situation where the number of observation is much more greater than the number of predator. We expect the ordinary least square to perform wonderfully well. Okay, now in that situation, there will be low bias, there will be low variance, and the model will be highly interpretable. You know, when I say low bias, what do I mean by low bias? You know, what do I mean by low bias? Because one of the properties of an estimator in statistics is that our estimator should be unbiased. Unbiased in the sense that we expect that the expected value of beta 1 cap will be equal to beta 1. The expected value of the estimate of that should be equal to the true parameter of beta 1. Now, you know, in the scientific world generally, okay, we normally pursue what I call an explanatory goal. Explanatory goal means we basically want to understand the world. We want to explain the world. We want to look at the effects of a variable on another variable. When you are looking at that, you are actually pursuing what I call an explanatory goal, which we also call Cosa goal. Okay, we call it a Cosa goal. Now, when you are pursuing a Cosa goal or an explanatory goal, okay, then your model needs to be interpretable. But the only way your model can be interpretable is when you don't have a lot of predators in your model. Because if you have so many predators in your model, okay, do you know why you are having so many predators? Because the belief is the more predator you have, the less is the bias. I'm going to say that again. If you want to guide against bias, you know what we do in statistics? Guiding against bias, you increase the number of explanatory variables in your model. But when you do that, you are creating a problem, because when you have low bias, a low bias will lead to high variance. You know what I mean by high variance? Your model will overfit. Overfitness is caused by having so many variables in your model. You are trying to get out of a problem, but you are creating a new one. Take a look at that. Okay? So, but this has been argued. If your goal is prediction, okay, let me tell you this. There are two different goals. One is an explanatory goal. The other goal is a predictive goal. The two are not the same. Okay? In the machine learning world, where they make use of big data, you know, when you want to talk about big data, okay, you don't expect number of observations to be greater than the numbers of predators. At times, if you're talking in gene sequencing, you could have so many predators, even more than the number of observations, even in financial series. In that kind of situation, OLS is going to break down. Does that make sense? Now, in that kind of situation, maybe your interest is not on explanatory goal. If your interest is not on explanatory goal, if your interest is on predictive goal, you are fine. Does that make sense? So what I'm trying to tell you, when you have so many predators in your model, okay, your model will not be able to interpret your model. You get a lot of predator. But when you have a lot of predators in your model, that will help your predictive goal. And that is why in machine learning world, they don't care about effect of a variable on another variable. What they care about is what is the combination of variable that will give us the best prediction. So there are two goals: explanatory goal and predictive goal. Okay, so but in a modern day world, we are looking for a way to translate an explanatory goal into predictive goal. That is what we have in mind now. Okay, when the numbers of observation is much more equal the numbers of predator, I said the least square feet will have high variance, and that will result in overfitting. Okay, overfitting leads to poor predictions. Let me tell you this: when you have your set of data, you're gonna split that, right? We're gonna walk you through splitting data. Okay, you're gonna split your data. Okay, we're gonna split your data into training, sets and test sets. Okay, now in a situation where you have the numbers of observation equal, much more equal the numbers of predator, you know, in a situation where you have that, your model will perform greatly on the training set, but will perform poorly on the test set. It means your model will only perform greatly on the data set you are seeing now. When you introduce a new data, your model will perform poorly. You know why your model is performing poorly? Because your model consider a lot of explanatory variables. When you consider so many explanatory variables, your model will capture noise. Your model is going to capture noise. You understand what I mean? Which means your model will capture error. In our model, we don't want to capture error. The moment your model capture noise, your model will perform excellently on the training set, but will perform poorly on scene data, and we don't want that. Does that make sense? That is what I want to say. High variance will lead to poor prediction. High variance is where you have a lot of variables in your model, even though you have low bias, but you have high variance. If you have low bias and high variance, okay, if your goal is explanatory, okay, the issue that you're going to have is that your model may not be interpretable because you got a lot of variables. And if you have a lot of variables, okay, it will lead to high variance because your model has captured noise. We only what we expect your model to capture only is signal, but your model is capturing both signal and noise. That's not good. And that is why it's going to perform excellently on the training set, but it's going to perform poorly on the test set. So take a look at that. Now, what if in a situation where the number of observation is less? Okay, in that situation, of course, the variance will be infinite and the multicollinearity is unavoidable. I told you yesterday, multicollinearity is one of the problems that we have in multiple linear regression, and multicollinearity need to be addressed. Multicollinearity is a situation, what could lead to multicollinearity is when you have a lot of variables in your model. There will be possibility that some of them may be correlating. Does that make sense? Okay. Now, whenever there's a problem, there should be a solution, right? But there's a way out. Now, the way out, number one, is using subset regression. What do we mean by subset regression? We're not going to use all of that. We're only going to settle with a subset. Does that make sense? When you are settled with subset, it means you have succeeded in eliminating irrelevant variables. Why do I want to tolerate so many variables in my model, and some of them are even irrelevant to the response? Why not discarding them? That is what the subset regression is talking about. The second one is talking about shrinkage. You know what I mean by shrinkage? If I have so many predators in my model, let's say for instance, I have 10 predators. How many slots am I going to have? 10, right? Now, the shrinkage, you know what shrinkage approach is going to do? It will shrink the magnitude of the estimate to zero. When the magnitude of the estimate, when the slope is zero, what does that mean? It means that particular variable is irrelevant. We have an approach in statistics that we can, that one of the approach that will help us in the shrinkage. I don't know whether you've heard about lasso. Has anybody heard about lasso? Lasso regression? Okay, lasso is one of them. Lasso. Okay, we call it lasso regression. You can search it on Google. And another one is what we call ridge regression. These two regression techniques, okay, will enable us to shrink the coefficients of irrelevant variable to 0. Does that make sense? Now, and the last one is what we call dimensionality reduction. Has anybody heard about principal component analysis? Anybody? Principal component analysis? Okay. So what we use in achieving that is what we call principal component analysis. Okay. When the numbers, when you have it, when the numbers of independent variables is so large, there's so many. Okay. If I basically want to reduce, okay, the dimensionality, of course, we're going to make it a principal component analysis. So there are different way out. That's what I'm displaying to you now. Okay, I want to go into what I call model interpretability. Let me tell you something. I told you the other time, we pursue two goals in statistics. Okay, let me tell you this. Frankly speaking, statisticians, psychologists, sociologists, economists, everyone in the scientific community will pursue an explanatory goal. Okay, but the predictive goal is left to the industry. Even there was a time scientists believe that if you want to talk about prediction, okay, that the only thing they do is they basically try to understand what has happened in the past. When you understand the world, you can explain the world, but the fact that you can explain the world does not mean you can make a prediction of the future. I'm going to give you an example. This is a car. It's a car here. Okay. The fact that this car has a gas in it. Okay. If a car has a gas in it, does that mean I can predict where that car is going to go? I may be taking in mind that the car is going to go to Minneapolis, but before you know, the car is in Chicago. I may be able to understand how car work. Somebody who manufacture a car, right? Okay, understand how the car work, but it can never predict where the car will go. So model explanation is different from model prediction. Does that make sense? So it looked like in the scientific community, they pursue explanatory goal. Okay. But in the industrial world, okay, it is predictive goal. There's a difference between the two. But what we do right now is it's not as if we don't make a prediction using statistical model. We make a prediction using statistical model, but let me tell you, the prediction with a statistical model does not have a huge power compared to when you use the machine learning algorithm. But when you use machine learning algorithm, you cannot interpret. Does that make sense? You can't interpret using machine learning algorithm. No interpretation. Interpretation is lost. You know why? Interpretation is lost. There's so many variables. Does that make sense? Okay, when P is large, okay, you have a large numbers of variables. The OLS is not interpretable. That's what we mean. Now, there will be some variable among them that have no effect. If they have no effect, you know what I mean? They are irrelevant. There's something need to be done. We can shrink the coefficient to 0. We can do whatever. Now I said the model will be easier to interpret if we remove the unimportant ones. Look at where I'm coming now. If you want to make your model to be interpretable, what is the essence of estimating parameters of a linear regression, but in the end, you cannot interpret? That's an exercise in futility. And that is the reason why when you have so many independent variables, okay, then the interpretation will be difficult. And what you need to do, why can't you look for a way to prune down the numbers of predators in your model? That's exactly what I mean. Okay, that means their coefficient will be 0. And when the coefficient equal to 0, you know what that means. Okay, when the coefficient is 0, then it means that predictor is irrelevant. Now let's look at the shrinkage. Okay, I put later lessons. Okay, the shrinkage is, in the shrinkage we use lasso regression, we use rig regression. The idea behind shrinkage is this approach will automatically shrink the coefficient of irrelevant variable to 0. But let me tell you this, lasso, we take a look at lasso regression, we do that. But for the ridge regression, the ridge will not shrink it to 0. Okay, but we know what ridge is going to do. It's still going to retain irrelevant predators in your model, but their p-value will not be significant. Does that make sense to you now? The difference between the two, I'm going to say that again. The two of them perform shrinkage. Okay, lasso, okay, we shrink the coefficient of irrelevant predictor variable to 0, which means after the analysis, they will be completely eliminated. They will not be part of the output. But as for ridge will still retain them, but when you look at the p-value associated with them, the p-value will not be significant. Does that make sense? The p-value, they're going to have a relevant variable. We have a p-value greater than 0.05. When the p-value is greater than 0.05, you know what that means? Insignificant. Does that make sense? So that is it. Now, dimension reduction. That is the case. That is where we use the principal component analysis. Okay. This approach we enable the correlated independent variables to be uncorrelated at the end of the day. But this approach also has issue. Okay, this approach has issue. Okay, I'm going to discuss this as time goes on. We're obviously going to talk about that. Okay, let me now come to subset selection. Okay, when in mathematics, when you have a set, right? When you have a set, okay, like for instance, you actually have a set as elements, right? You have a set, okay, a set as elements. Let's say 1, 2, 3, for instance, right? Okay, you may want to figure out what is the power of a set. In mathematics, the power of a set, okay, is going to be 1. You're going to have 1, 2, 3, okay, 1, 2, okay, 1, 3, okay, 2, 3, okay, 1, 2, 3, okay, and empty. Do you remember what you done in maths? Power of a set, we call this power, because the idea of the power of a set will be used in the subset selection. Okay, so this power of a set, you know what power of a set means? The possible number of subsets in a set. That's what it means. Power of a set means the possible number of subsets. Okay, take a look at this. And the formula is going to be, if I want to know, say 1, 2, 3, 4, 5, 6, 7, 8, the formula is going to be the power of a set. If I want to know the cardinality, okay, it's going to be 2 raised to power cardinality of the sample space. The cardinality means how many elements do you have in the sample space? 3, right? That is going to be 2 raised to power 3. That is going to be 8, right? Now, take a look at this. If I have 3 independent variables, can you hear me? If you have 3 independent variables, you know what I'm trying to say? You're going to have the possible numbers of competing models will be 8. That's what I'm trying to say. Model 1, you're only going to use 1 variable x1, 1 variable x2, 1 variable x3, 2 variables x1, x2, 2 variable x1, x3, 2 variable x2, x3, or you even make use of all. Can somebody tell me this? Empty? Which module is empty? Oh, look at me. Good job. Intercept. Send me a message for extra credit. Which is the intercept. Intercept is the most simplest form of a module. So which means if I have three variables, the possible modules, the possible subset of modules is basically going to be 8. That's what we want to talk about now. Look at that. Do you see 2 raised to the power p? Look at that. 2 raised to the power p possible modules. Do you see that? The only issue with this, is when the number of predator is large. Imagine if the numbers of predator I have is 1,000. That would be 2 raised to the power. That would going to be a lot of modules. Does that make sense? We're going to consider a lot of modules. Then from there, we're going to choose the best. Now that was why I said I said identify a subset of videos that we believe to be the most related to the response. Why? The advantage is that produce a smaller linear model. But what is this advantage? Finding the best subset is a combinatorial problem. There's going to be a lot of model, okay, when the number of predator is large. Okay, so that is it. Now, I want to go into these two, module complexity versus module fitness. You know, researchers, they've committed some blunder in the past. You know, at times it's going to look as if our modules are failing us. Our modules are not failing us. We are the one that we're not doing the right thing. They say, you know, some researchers, some statisticians normally find it difficult to differentiate between module complexity and module fitness. Before today, you know what we've been considering? We've been considering module fitness. Okay? But when should we consider module complexity? We're actually going to consider module complexity when the number of independent variables is more than 2 or 3. Does that make sense? When you got a lot of predator in the module. Let's take a look at that. Okay. What do you think we want? We actually want a simple model that can capture the relationship. Does that make sense? We don't want complicated model if possible. Does that make sense? Okay. Now, let's take a look at this. What are the criteria for model fitness? Of course, you know, what criteria do you think we'll be using? R squared, which we call the coefficient of determination, and the residual sum of square. Does that make sense? Those two are, you know, criteria for module fitness. Of course, a module with, take a look at this. What answer the question? When the residual sum of square is very small, that module is great. When the R square is large, that module is great. Does that make sense? So the residual sum of square is unexplained. We always want to minimize that, you know that, and we want to maximize R squared. Okay, so look at that. Dash ROSS mean the model fit the sample data better with smaller ROSS. Dash R squared mean the model fit the sample data better, the larger one. Does that make sense? Okay, these two criteria, they are only for module fitness. They don't work for module complexity. When you read an article and you have a lot of predator, and the researcher is using these two as a criteria, okay, to adjudge the module to be valid, that is misleading. Does that make sense? Okay, now take a look at this. K here is the numbers of regressors. You know, I told you the other time, what is different between regressors and predators? Regressors equal to numbers of predator plus 1. Where is the 1 coming from? Intercept. Does that make sense? If a module has 3 predators, then that module has 4 regressors. Does that make sense? Okay, so what actually measures module complexity is the numbers of regressors that you have. Why are we using regressors here? Why are we not using predator? We're using regressor because when you are working with a polynomial, For instance, you work with polynomial of degree 2 in one variable. You know, you still have one predictor, right? But the regressor is much. Regressor is going to be 1x squared for polynomial of degree 2. Does that make sense? Okay. Now, what determines module complexity is actually the number of regressors. Okay. Now, but the smaller k means what? The module is very simple. Does that make sense? Okay, that's what it means. Okay. Now, another thing I want you to see. Take a look at this. The first one, you fit a linear regression, right? Where k equal to 2. What is k equal to 2? Beta not beta 1, right? K equal to 2. And RSS, okay, is 0.403. By the time, look at the one in the middle. The one in the middle, what is that? What module is that? Intercept, right? Okay. What is the RSS? 4.99. Of course, the RSS of that one is bigger. So that's a poor one. Okay. K equal to 1 means 1 intercept. By the time you move to what degree of polynomial is that? Degree 4, right? Degree 4. How many regressors? 5. Okay. What is the RSS? 0. We don't want this one. You know why we don't want that one? That is over fitness. That has captured noise. When RSS equal to 0, what does that mean? You don't have a statistical model anymore. You are telling the world your model capture exact reality. That is not possible. Your model cannot capture exact reality. That is over fitness. Does that make sense now? Okay. So we don't want intercepts. We don't also want situation where there's going to be a lot of regressors in the model. Does that make sense? Okay, take a look at this. You remember the other time I walked you through a real life practical situation where I'm actually looking at the effect of experience of a professional workers on their salary when we fitted simple linear regression. Okay, the RSS was that, the R square was that. When we fit first order polynomial, second order, and so on like that, what happened? You're going to see that the more when you increase the order of the polynomial, the RSS is going to be going down and the R square is going to be going up. What do you see? You see that? The RSS is going to be going down, decreasing. Then the R square is going to be increasing. Take a look at that. Let me tell you this. Even if what you are adding doesn't make sense, the R square is going to continue to go up. In that situation, we cannot trust our R square anymore. Does that make sense? Okay, because the module is becoming complex. R square is only adequate for module fitness, but it is not adequate for module complexity. Therefore, the R square need to be adjusted. And when R square is adjusted, then it becomes adjusted R square. Does that make sense to you now? Okay. Now, I just asked a question. How did the RSS change when we had more polynomial regressor? Of course, the R square is going down. I mean, the RSS is going down. RSS residual sum of square will continue to decrease. Okay. Then what about R square? The R square is going to be increasing, even if you are adding a regressor that doesn't make sense. R square has a tendency to be going up. And that is the reason why R square cannot be trusted anymore. If that cannot be trusted anymore, now take a look at this. Because of that, then what is the criteria of module selection? Okay. The criteria for module selection, what did I say? It should be the one that consider both module fitness and module complexity, not only module fitness alone. Does that make sense? Okay. Now, you already know criteria for module fitness. What are the criteria for module fitness? Residual sum of square and R square. Does that make sense? And I said two of them cannot be trusted when in the case of module complexity. What do I mean by module complexity? When the numbers of regressors in a module is large. Then what are the brand new criteria that we actually need? Oh my God. This, if you take a look at these three criteria now, they are good for both modal fitness and modal complexity. Take a look at that. The first one is adjusted R squared. The second one is a Kaike information criterion that we call AIC. And the third one is a Bayesian information criteria that we call BIC. Okay, these are the model selection criteria we basically going to use. The highest, well, we always want to maximize adjusted R square, okay, and we want to minimize AIC and the BIC. Does that make sense? We want to maximize adjusted R squared. We want to minimize AIC and the BIC. Okay, now what is the formula of the adjusted R squared? Oh, look at that. That is the formula of adjusted R squared. You see that? It is just, if you take a look at the other side, you're going to see RSS, right? Divided by SST. Okay, take a look at that. It means to be able to have adjusted R squared with modified residual sum of square. You see the residual sum of square? Because initially, residual sum of square was just a module, was just a criteria for modal fitness. And if I want a criteria for both modal fitness and modal complexity, what I'm going to do is to actually modify that. Take a look at that. Then I have some questions that I expect you to, as you increase your K, what is the K? Okay, K is the number of regressors. You can look at the mathematics. What is going to happen to SST? What is going to happen to n minus 1? You can figure that out later. Okay, now that is criteria number 1. Okay, what is the rule? The module with the largest adjusted R square is the best module. Okay, when you have more than one module, the module with the largest adjusted R squared is the best. Now, what about the second criterion, the BIC? Oh, I mean the AIC. Oh my God, the AIC. What do you see in the formula of the AIC? What you see is RSS. Can't you see? For adjusted R square, we modify RSS. For AIC, we also modify RSS. Take a look at that. Okay, so this is the formula for AIC. N is the number of observation. RSS is the residual sum of squared, and K is the numbers of regressors. I ask a question there. Take a look at that guy. Okay, what is the rule of thumb? The module with the smallest AIC is the best module. Please take note. Module with the smallest AIC is the best module. So take a look at that. Okay, now the criteria here that we have introduced, put into consideration modal fitness and modal complexity. Okay, at the same time. Now let's look at the BIC and what is the coding now? The coding now is going to be extract AIC. Like for instance, you fit a regression model, right? If you fit a regression model, okay, if you fit a regression model, okay, and you call it maybe MOD equal to LM Y on X, right? Okay. Now, if you just write extract AIC MOD, it's going to give you the value of AIC. Okay. My TA is going to walk you through that. That's what you're going to do in the lab tomorrow. Okay. Now, for the BIC, oh my God, look at the BIC. You see, we'll see have RSS in it. Okay. The difference between this and that one is that we have a log n K, but in the case of AIC, it is 2K. Let's go back. Do you see 2K? That very 2 was replaced by log n in the case of BIC. Okay. And you know what? The rule of thumb is also pick the model with the lowest BIC. Okay. What is the coding now? If you want to extract BIC in R, you're going to write extract AIC. After putting a module name, you're going to write K equal to log n. Do you see that? That is the code to extract BIC in R. Take note of that. Okay, so take note of that. Now, all these criteria actually combine both module fitness and module complexity. Okay, take a look at this. Maybe you run these four modules. Okay, X is experience, Y is salary, and for each you obtain the AIC, BIC, and adjusted R squared. Okay, so the module with the largest adjusted R square is the best, and module with the lowest AIC or BIC is the best, but at times there could be conflicts. Okay, the AIC and BIC agree here. What module do they choose? The AIC choose quadratic. The BIC also choose quadratic, but the adjusted R square actually choose cubic. Do you see that? You see cubic, polynomial of degree 3. Okay, in that kind of situation, we're going to go with AIC and BIC. That is why we have more than one judge in the Supreme Court. Okay, go ahead. Exactly. That is why we have, in the United States, they have 9 judges in the Supreme Court. At the end of the day, what are they going to do? They're going to vote 5-4. There can never be a tie. Does that make sense? That is why they make it odd. If it is even number of judges, what is going to happen? There could be a tie. Okay. Now, okay, that was what I was trying to say. Often, this criteria identify different module as the best. Go ahead. What are if they all? It's not possible because the AIC and the BIC, they will always like moving together. AIC and BIC. Go ahead. Yeah, actually, in the other one, you know, the normal R square will always increase. But if you take a look at the adjusted, right, instead of increasing, this is optimal. That's why we call it adjusted. It has been adjusted. So this can be trusted. Does that make sense? Yeah. Okay. Now, I've walked you through criteria for module selection, as you can see. Okay. The next thing now is selection method. Okay, they're different between the two. Criteria is different from the method that you use. In the method that you use, you're actually going to be aligned with one of the criteria. Now, let's look at the success selection. Are you surprised with this? Give me 1 second. Are you surprised with this subset? That was the one I demonstrated the other time using power of a set. If you have how many x1, x2, x3, what will be the possible numbers of modules? 2 raised to power 3 is going to be what? 8. Look at the first one. Intercept. Count all of them. How many modules do you have? That is 8. Do you see that now? This is what we call off subset selection. Okay. Among this now, we want to choose the best module. Okay. Now, it has a strength. The strength is that it will give us opportunity to go through all the modules and figure out which one is the best. But the weakness is that what if the numbers of regressors is large? Okay, that would be expensive to go through all the modules. Does that make sense? Okay, now we now have another one approach that we call stepwise method. Okay, the stepwise method can be backward, can be forward, and can be both direction. Okay, I'm going to explain to you now. We have a backward elimination. The meaning of backward elimination. I will start with a complicated module, and I will be eliminating the irrelevant one. But the forward selection means I'm going to start with nothing. I will start with intercept, and I will start adding the relevant one. And the both direction is the one that proceed. Both direction. Okay. Now I'm going to show you something now. I want to do backward elimination with AIC. You know what I mean? I have 3 predictor, and I want to be moving backward, removing the irrelevant one, right? I'm going to start with the complicated. What is the complicated? Where I use all the variables. I'll get the AIC. What is the AIC? Negative 112. After the AIC, if you look at it where I start, I use 3, right? Then in the second one, what am I going to do? It's going to be 2. X1, S2, right? S2, S3, and X1, S3. Do you see that? Now, if I'm going to be looking at in step 1, which one has a lower AIC compared to where I start? Okay, which one? Okay, negative 116 and negative 119, right? But we're going to choose negative 119. That is the most smallest. Does that make sense? So what are we choosing now? We are right now, it's an algorithm. We're choosing that guy. Okay, we're choosing the one for X1 and S3. Now, after choosing the one for X1 and S3, you know what we're going to do now? We will now consider a model with one predator, and one of the predator will be X1 because you have X1, S3, right? The other predator is going to be X3. Do you see that? Do you see that? Now, we're now going to look at the AIC again. Which one has the smaller AIC compared to negative 119 is the one for X3, right? Then you're going to choose the one for X3, okay? After choosing the one for X3, what is the next to compare with? Nothing. Intercept, okay? Now, intercept, you look at the AIC of the intercept. The AIC of the intercept is greater. Therefore, we have reached an optimal solution. What is the best model? The best model is the one with the S3. Any question? This is how backward elimination with AIC work. I can also do backward elimination with BIC. I can also do backward elimination with adjusted R squared. Okay, so take a look at that. Okay, now I'm going to quickly do forward. Oh, forward. In the forward, I'm going to start from the nothing. Right? Forward. I want to move forward, right? I'm going to start with nothing. I'm going to start with the intercept model, compute the AIC. After nothing, I'm going to go to 1-1 predator. You see? Okay, 1-1 predator. Which one has the smallest AIC? The one of S2. After the one of S2, I'm going to consider the model with 2 variables that has S2 in it. S2 and S3, S2 and S1. Okay, there's no any other one. Okay, I'm looking for the model that has S2 in it. Okay, now I have this one now. What am I going to do now? Which one are the smallest AIC compared to negative 125? Is this guy here. Okay, now after that, the next one that I'm going to consider now will be intercept model. Now in the end, what do you see? The best here is X3. Now, I wanted to take a look at this now. Backward elimination with AIC selected X3 model with X3. Why the the forward selected that and this selected that. You can see a kind of conflict between them. This is the backward elimination selected that. Okay, so take a look at that. And when the backward selected that one, and the backward elimination means the best model, because actually the best model is the one that has the smallest AIC, which is X2. So which means the approach can skip the best model at times, and that's why we need other approach. My TA is going to walk you through. I think I provided some arrow code. Look at the arrow code. Okay, all this arrow code. This is what my TA is going to walk you through tomorrow in the lab. Any question? All these are what my TA is going to walk you through. How do you perform stepwise selection with AIC in R? What I just explained now, the algorithm I just explained now, my TA is going to walk you through all of that. Is there any question? Is there any question? Look at this is very interesting. They rate my professor. You look at the first module, second module, and all of that, you get the AIC. Okay. Now, the first one, quality on clarity, is the best one predator module. That's what it's telling you. There's so many one predator module. You get what I mean? Among one predator module, they choose clarity. Among 2 predator module, they choose clarity and later interest. Does that make sense? Then these are the best. Then among the best, choose the best. That's what we're going to do. That's going to be the lowest of that is what is now. This is what we call the up subset selection. Up subset. Okay. And you now consider the stepwise. This is the stepwise. The backward, this is a cardinal. The forward, this is a cardinal. How many? One up subset selection, backward, and forward. Okay. That's what I walk you through today. Okay. Any question? MIT walk you through how to implement that now. Okay. Make sure you all stay safe and have a very nice weekend. So bye for now. Everyone, see you on Monday. You're welcome. You're welcome.